we have seen that in an inviscid irrotational flow, the lift produced by an airfoil or a body is proportional to the circulation around it, and what we have found that the drag force is 0. Of course, in a 3-dimensional inviscid irrotational flow, the drag force is not 0, as you will be seeing later that a drag force comes in, but as far as 2-dimensional geometries are concerned, the drag force is invariably 0 if the flow is inviscid irrotational. Now, this is of course unrealistic, as is known from experiences that all bodies experiences drags. The lift may or may not be there, but the drag force is always present. Also, in case of lift, we see that the lift is proportional to circulation, and if you remember Kelvin's circulation theorem, which says that rate of change of circulation around a material closed curve in a fluid of uniform density, in which the body force is derived from a scalar potential, is 0 in an inviscid irrotational flow. Now, then a question comes that if the lift is proportional to the circulation, where does this circulation comes from? Where does this circulation comes from? We used an artifact of Kutta condition to fix the value of circulation. We say the Kutta condition will is such that the flow will leave the trailing edge smoothly. So, this is the artifact that fixes the value of circulation, but the question that where the circulation comes from still remain unanswered. So, in both the question of lift and drag, that inviscid irrotational flow cannot answer what are required. It cannot answer where the circulation comes from. It gives the value of lift correctly, that it is proportional to circulation and it is rho q gamma, but correct. But how the circulation comes? If we when we place a body in an uniform flow is irrotational, as you can see clearly by taking the curl of that uniform flow, is all gradients are 0. So, curl is also 0, that is rotation 0, no vorticity. See, if the vorticity is 0 to start with, then if we consider any material closed curve, across that material closed curve the circulation is also 0, and an inviscid irrotational flow, the rate of circulation, rate of change of circulation around any material closed curve is 0. So, what was 0 initially, that will remain as 0. So, how that circulation comes in? Now, to answer these questions, or rather to some of these questions to start with, we need to look into say the viscous flow or irrotational flow to find the answer. And since we are talking about vorticity and circulation, let us see the vorticity and circulation within the framework of a viscous flow. Of course, we will still retain the assumption of incompressible flow. So, next couple of lectures we will discuss how a viscous rotational flow answer these questions. If we what will vortex dynamics? Now, vortex dynamics on its own is a subject you can call. So, of course, we will be discussing some preliminary aspects of vortex dynamics. I hope you remember that we earlier derived the Navier-Stokes equations or the equations of motion in the form of vorticity, which we named as vorticity transport equation. To remind you once again, the vorticity transport equation was, which you remember that it was obtained simply by taking curl of the Navier-Stokes equations. Now, this equation shows how the vorticity at a point is likely to change. The first term on the right hand side simply gives that the vorticity may be or vorticity can be convected with the flow itself. That means, the flow can carry away the vorticity along with it. The second term, if you remember, we described at that time is rotation and stretching of the material vortex element. Also we said that this effect is a secondary effect, it simply redistributes the vorticity locally, it redistributes the vorticity locally. It does not change the broad feature of vorticity distribution over the entire fluid. And the last term is vorticity diffusion. Then it shows that vorticity can be spread from one part of the fluid to the other part by simply the action of diffusion by viscosity. That is, if there is a vorticity at certain places, the viscosity can diffuse it to other part. But perhaps that itself is not sufficient to answer how the vorticity comes in the first place in the interior of a fluid which is moving uniformly. When the fluid is moving uniformly, there is no vorticity. Now, this term, this viscous action or viscous diffusive action can spread vorticity once it is there. So, it still does not answer how it comes. Same thing about circulation. If you remember, we derived that rate of change of circulation or this equal to 0 in viscid incompressible irrotational flow. But if you in deriving this equation, if you remember that we consider the definition of circulation, the line integral of velocity about a material closed curve, and then we differentiated it. And for the term du dt, we replaced the incompressible inviscid Navier-Stokes equation or the Euler's equation. You can derive the same equation, but replacing du dt not by the Euler's equation, but by the complete Navier-Stokes equation, retaining the viscous term, and then this will give a term something like this. Something like this. Okay. That is, once again it shows that the in a viscous flow, the circulation around a material closed curve can be changed due to again the diffusive action of viscosity. But how the viscosity or sorry how the vorticity comes in or how the circulation comes in, it has to be there, only then it can spread or diffuse. Now, let us see it from other way, considering the flow. I think we discussed it once earlier, but let us do it once again. Consider a motion starting from the rest. To do that, let us think about a situation where we have a body immersed in a fluid at rest. Body is immersed in a fluid at rest, and let us for simplicity once again consider that the fluid is of uniform density, the body force is derived from a gravitational potential from a scalar potential like gravitational force, and then imagine that the body starts impulsively from a velocity 0 to some velocity u and then moves steadily with that velocity. It changes impulsively from 0 to u and then moves with that velocity uniformly. What is likely to happen? The instant the motion starts, the solution of this flow will be invariably invisibly rotational. The instant, just think about that instant when the motion is starting at t equal to 0, let us say that is t equal to 0. As long as the fluid is at rest, obviously viscosity has nothing to do, viscosity has no role to play. Even if the fluid is viscous, the viscosity has no effect because the fluid is at rest. Viscosity acts only when the motion starts. So, just at the start, this motion will start as irrotational, and since at before t equal to 0 there was no vorticity within the interior of the fluid, then at t equal to 0 also there will be no vorticity in the interior of the fluid, But consider the next instant t equal to 0 plus, that time the motion has started. So, viscosity has started playing its role. And what is the role of viscosity? It enforces a no slip boundary condition. At t equal to 0, when the motion starts, this motion was inviscid irrotational, and you know that inviscid irrotational flow is completely obtained by 0 normal flow boundary condition, which gives a slipping motion. So, at t equal to 0, when the motion starts, the motion is slipping motion. The fluid over the solid body slips at t equal to 0, but then at t equal to 0 plus, the viscosity has started playing its part. What it wants? It wants that the no slip boundary condition must be satisfied, there must not be any slip. Then see, at t equal to 0, what we had initially? There is a jump in velocity. On the solid wall, there is a jump in the velocity. The fluid layer adjacent to the solid body was moving with the velocity u. If we consider the relative velocity is u. But at time t equal to 0 plus, this relative velocity must cease, it will become 0. What then happen? A finite seat of vortex, because there was a jump in velocity at t equal to 0, that has created a seat of vortex at t equal to 0. So, this is the mechanism of generation of vorticity in the first place, the no slip boundary condition on the solid wall, that at t equal to 0 plus creates a seat vortex. If you remember that we discussed earlier about seat vortex, and we show that across a seat vortex there is a jump in tangential velocity. We consider a seat vortex. On the lower surface we had a velocity of gamma by 2 in one direction, on the upper half gamma by 2 in the other direction, giving rise to a jump in velocity equal to gamma, the strength of the vortex seat or the circulation about the vortex seat. So, here also there is a jump in tangential velocity which is equivalent to a seat vortex. So, as the body starts moving at t equal to 0, a seat vortex has developed on the surface of the solid body, not in the interior of the fluid, not in the interior of the fluid, it is generated on the surface of the body or at the boundary. The solid wall is one of the boundary, the other boundary let us consider at infinity where the fluid is at rest. So, there is no question of any vorticity coming through that boundary. So, this is also another way this can be answered, that according to this vorticity transport equation or circulation Kelvin's theorem, if there was no vorticity or no circulation in the interior of a fluid, it cannot be created there. So, it must have to come from boundary itself. If the vorticity cannot be created within the interior, then it has to come from the boundary, and we see that is how it is produced at the boundary. So, now considering the motion from rest, we can explain this development of this motion in 3 stages, one at time t equal to 0, one at a small time after t equal to 0, and then one at later. So, you can consider the alternative case also, that the fluid started moving impulsively, the body is held fixed, it is all the same. We have 3 stage development. The velocity changes from 0 to let us say u, subsequently moves with u. At t equal to 0, the flow is irrotational. Sorry. highly concentrated seed vortex, because the velocity gradient is almost infinite. So, at viscosity starts playing its role, what is its role? To diffuse or spread this vorticity. Once the vorticity is created, that seed vortex, now viscosity can of course do its bit, it can try to spread that. That is the vorticity which was created on the surface of the body, that vorticity is now spreads towards the fluid. That viscosity can do. Once it is there, it can spread, it can diffuse. However, there are two other mechanisms or two other effect on vorticity. One is the vorticity is also being convected and also being modified by stretching and rotation. But as you have considered that, or as you have mentioned, that stretching and rotation is basically a local redistribution, it does not spread. So, let us consider only the main two action, the convective action and the diffusive action. Now, in the initial stage, when the time is small time, if you remember, we earlier considered this problem, a flat plate starting impulsively, and we saw there that the vorticity spreads at time t by a distance of nu proportional to nu t to the power half, root nu t. The distance to which vorticity is spread is root nu t. You can look back, only because of this we took up that problem at that time, a flat plate started impulsively. So, this nu is the kinematic viscosity and t is the time. So, after time t, because of viscous action, the vorticities can spread up to a distance of nu t to the power half. Nu t has a dimension of length or length square. What is the dimension of nu t? Nu is kinematic viscosity, mu by rho. Okay, nu t has a dimension of square of length, so it is square root, that is what is proportional to the length. You can consult that earlier solution of impulsively started plate. That example of impulsively started So, after a small time t, because of this viscous action, the vorticity which was initially created on the surface has now spread to a small distance nu t to the power half. However, the convection is also simultaneously playing its role. Now, if we consider our flow, this flow was supposed to be tangential. When you start a body moving through the fluid which was at rest, this flow, fluid flow will be mostly tangential. Of course, there will be a normal component also, but after a small time or at a small distance from the body, the normal component of the velocity is likely to be small. That is, the flow velocity is essentially tangential with a small normal component at best. Now, if the flow velocity is the normal component of flow velocity is small, then the convective action is predominantly in the tangential direction. Diffusive action is in all direction, while the convective action is predominantly in the tangential direction, but have a very small or negligible contribution towards the normal direction as well. So, that is the situation at a small time, that the vorticity is now being spread to a distance of nu t to the power half and simultaneously is being carried away by the convection, and the normal spread by the convection is practically negligible. Now, consider the time which is large enough, not small, a large time. By large time, what is likely to happen? There will be balance of, and consider the situation where the flow reaches a steady state, that is further no change in time, it has reached a steady state. Means what? That these three contribution of vortex motion, convection, local redistribution through rotation and stretching, and diffusion, these three has reached a balance. These three has reached a balance. Once again, that the second action, local redistribution by stretching and rotation, is a secondary effect. It does not alter the global distribution of vorticity, it is a local effect. So, once again neglect this. So, it is the relative contribution of convection and diffusion. Of course, this relative contribution or the balance of these two contribution changes from flow to flow. There are some flow problems which is quite a majority of the flow problems. However, you can see that there is an opposition between convection and diffusion. Of course, not always. In some cases, in some flows, there is a opposition between convection and diffusion. First thing, that the forward motion, in either case, if we consider the forward motion of the body or the fluid is moving over the static body, in each case the convection is opposing diffusion in the forward direction. A body is moving like this, the convection is in this direction. So, our diffusive action is in this direction. So, there is a opposition in the forward direction between convection and diffusion. Even in the sideways, this side and this side, if we let us consider a flat plate, or if you think about an if the flat plate is moving in this direction or the airfoil is moving in this direction, the convection is in this direction, because the relative fluid velocity is left to right. If the body is moving from right to left, then the relative fluid velocity is left to right. So, viscosity is trying to spread the vorticity in the forward direction, right to left, while convection is trying to carry it from left to right. They are opposing each other. So, in the forward direction they are opposing each other. Similarly, in the sideways, viscosity is trying to spread it in this direction, viscosity convection is trying to carry it along with it. As we mentioned that the normal component of velocity being small, the convection towards the normal direction is much smaller than the convection in the streamwise direction. So, even on these two sides also there is practically an opposition between diffusive spreading and convective spreading. Okay. However, when we come to the rearward direction, backward direction, then you see that they support each other. Convection is also trying to carry it from left to right, and viscous action is also trying to spread it left to right. So, they are supporting each other. From this, what we can see that if the convection or the convective force or the inertia force is much larger than the diffusive force or the viscous force, then convection will force the vorticity to remain confined very close to the body itself. If convection is dominant or much stronger than the diffusion, in the forward direction it will not be able to spread much, in the sideways also it will not be able to spread much, only in the downward direction of course there is no opposition, that it can go to anywhere, let us say even up to infinity it will spread. But in the forward and sideway the spreading will be much small if the convection is much larger. However, if the convection and diffusion is of the same order, then the spreading will be much larger. So, this is when let us say this is to infinity. Only in this part that vorticity will remain confined because of the mutual action of convection and diffusion. However, if this will be the situation when say at the final steady state when the time is large. This will be the situation. Now, let us give it a little more definite meaning of that large time. Considering a problem which is reaching to a steady state, what should we call is a large time or time infinity? Consider a body of length L in the direction of the flow, the body length in the direction of the flow or the relative fluid motion, in the direction of the relative fluid motion. Let it be L. Then how long a fluid element is likely to reside in the neighborhood of the solid wall? Definitely L by u, what we have taken as the velocity. It is the characteristic velocity. So, this L by u can be taken as a very large time. What we call large time, that is of the order of L by u. Remember, we are talking about of the order of, the characteristic velocity is of the order of u. It is not that the characteristic velocity has to be u exactly, no. That we have seen earlier, that if we consider flow about a circular cylinder, the maximum velocity reaches 2 times the free stream velocity. In case of airfoil also it behaves like that. So, that velocity can become 2 times or 3 times is immaterial, but it is of the order of that. So, by large time, or we can consider that L by u is the large time. So, by large time we mean time t is of the order of we consider this time the velocity u or u infinity u. Okay. So, if you consider the spreading, how much will be the spread at large time? Nu t is the square root of nu t is the distance to which the vorticity spreads after time t. So, when time approaches to infinity, when t approaches infinity, that is of this order, then the spreading by viscous action is nu L by u. Okay. Now, whether this spreading is very small or of the order of the body length itself, okay, when will be this spreading will be of the order of the body length, body size, characteristic size of the body is L. If we need that, if we try to look for the condition at which the spreading is also of the order of L. So, we can say that the spreading will be of the order of L what What do we get from here? U L by nu is of the order of 1. So, this is of that, say U L by nu, this is the condition is of the order of 1. And if U L by nu is much larger than 1, spreading is very small, infinitesimally small. Or we can say the vorticity is confined within a thin region near the body surface. Now, let us see what is this U L by nu, U L by nu. Think about the Navier-Stokes equation. The convective forces are, or the convective force is given by the term U grad U. If you look to the Navier-Stokes equation, the left hand side is rho into du dt plus U grad U. When you write in your standard form, each term is U du dx, U du dy, V du dx, this sort of terms. Okay. That is what we call the convective acceleration. What is the order of this term now? Say we will consider force per unit volume only, or say force per unit mass, that better, then rho will not come into picture. Only U grad U, convective force per unit mass. Okay. What is its order? No, I am not asking for the dimension. This is an acceleration, you can say very clearly L by t square. This is the order of magnitude. The characteristic velocity is u, that capital U that we are using, and grade u is u by L. So, this has should we write order of. What is the viscous force per unit mass? What is the viscous term in the Navier-Stokes equation? Nu Laplacian u, when you divide by rho per unit mass, is nu Laplacian u. And its order? Again order of. So, what is the ratio of this inertia force and viscous force? See, that will give us the strength of relative strength of the convective force and viscous force. Earlier we said that the convective force is dominant. If the convective force is dominant, then this is what is going to be the situation. Now, how do we measure dominant? That one is much larger than the other. So, this is what is that quantifies. What it is now? This u L by nu or rho u L by mu, nu can be replaced by mu by rho. So, rho u L by mu, this is what is called the Reynolds number, is designated by Reynolds number. We have earlier come across this also, and we will usually denote it by R e. And then going back to that earlier condition, if Reynolds number is much larger, we earlier had this condition when u L by nu is much larger than 1, vorticity remains confined within a thin layer. So, u L by nu is Reynolds number. So, when Reynolds number is much larger than 1, And also you can see that as Reynolds number goes on increasing, the thickness of that layer becomes smaller and smaller. Okay. And you see, this is the assumption that was used to for that irrotational flow or potential flow, that if the viscous action is confined to a very thin region near the wall. See, when you consider the complete flow field and a very thin region there where there is viscous action, outside there is no viscous action. So, it would be a good approximation to consider the entire flow field to be inviscid and irrotational. And we saw that okay, it is justified to some extent, but not fully. So, this is the reason which is commonly called as boundary layer, the very thin region near the body surface where viscosity plays its role, where vorticity is non-zero and velocity is changing normal to the surface. What actually the spreading of vorticity means? Come back. Initially we had the vorticity was created only at the surface. It remained at t equal to 0, it was on the body surface. Then we said that which is equivalent to a vorticity, seed vortex. A jump in tangential velocity is equivalent to a seed vortex, and then this vorticity spreads. What actually spreads? This spreads that velocity gradient. When you said that the vorticity spreads, actually that velocity gradient is spread. Velocity gradient which initially occurred over a distance of 0. The velocity gradient that occurred at time t equal to 0 over a distance 0, that has spread to a distance of the order of the 1 by Reynolds number, or square of 1 of inverse square root of Reynolds number. That velocity gradient, that is the change from 0 to u, that change in velocity initially occur over a distance of 0, but as time passes or as viscosity plays its role, this change from 0 to u is now occurring not over a distance of 0, but over a certain distance, which is the distance is of the order of inverse square root of Reynolds number. That is what is the spreading of the vorticity means, that the velocity gradient or the velocity jump which was occurring basically as a jump is no longer as a jump, but it is gradually changing, smoothly changing over a distance from 0 to u. At the end of that layer the velocity is again u, but on the wall the velocity is 0. So, from 0 to u that change or that jump has been spread and now has become a smooth and continuous variation over the distance which is proportional to inverse square root of Reynolds number. And within that layer in which this velocity variation takes place, that is what is the boundary layer. So, for a high Reynolds number flow, a boundary layer develops over certain geometries, and within this boundary layer the velocity changes smoothly from 0 on the surface to the inviscid flow velocity at the edge of the boundary layer, the inviscid flow velocity at the edge of the boundary layer, and within this layer the vorticity is non-zero, the flow is rotational. And so, think that when the Reynolds number is really large, considering practical aerodynamics where Reynolds number is of the order of 10 to the power 7, 10 to the power 8, then inverse square root of that is practically very small. over a wing chord of say 2 meter or so, maybe the velocity boundary layer will be at a flying Reynolds number of the order of few millimeters. The maximum thickness of this boundary layer will be of the order of few millimeter. And you see that the assumption that the entire flow field is inviscid irrotational is in that sense justified. When you think about say meters of area or volume, just few millimeter is really negligible, but you see that has this effect, that gives the drag force 0, or in a 3 dimensional case non-zero, but still not correct, far away from the correct value of drag. So, this is the concept first brought in by Prandtl in more than a century ago in 1905, where showed that okay, you can use your inviscid flow analysis, but you must satisfy that no slip boundary condition. That means, you must bring in the boundary layer to bridge the gap.